In this video, we will find the intervals of increasing and decreasing concave up and concave down for these two functions. If you appreciate the content, please give it a like. As we do the first problem, keep in mind that the domain is limited to the interval from 0 to 2 pi. The first step to find intervals of increasing and decreasing is to find y prime. The derivative of x is 1, and we bring down the negative 2 and move on to the sine x. Memorized rule, the derivative of sine x is cosine x. So this is y prime. The next step is to find where y prime is equal to 0 or where y prime is undefined. However, cosine is defined everywhere, so we don't need to worry about this one. So let's set y prime equal to 0 and solve. Adding 2 cosine x to both sides, we get 1 is equal to 2 cosine x. Dividing both sides by 2, we get cosine x is equal to 1/2. But where is cosine equal to 1/2? Hopefully you long ago memorized these 9 trig facts, including the fact that the cosine of pi over 3 is 1/2. So pi over 3 is the reference angle. A reference angle is the angle between the terminal side and the x-axis. Every quadrant has an angle with a reference angle of pi over 3. The cosine of any of these angles will be some kind of 1/2, but the 2 on the right will give us a positive 1/2, and the 2 on the left will give us a negative 1/2. In this case, we want cosine to equal positive 1/2, so we will be limited to the 2 quadrants where cosine is positive. So in the first quadrant, the angle is the reference angle itself. This is the pi over 3. We can think of 2 pi, all the way around, as 6 pi over 3. So this angle is 5 pi over 3. These are the 2 critical values. X is equal to pi over 3, or x is equal to 5 pi over 3. Now it's time to make a y prime sign chart, putting our critical values in order from least to greatest across the top. Be sure to include the domain limitations at the beginning and end of the sign chart, and be sure to label the sign chart as y prime. This will only have one row since this is not something that could be factored. We need to decide whether y prime is positive or negative in each one of these intervals. To do that, we're going to use test values. For the first interval, we can use this value of 0 as a test value. Plugging in 0 gives us 1 minus 2 times the cosine of 0. Cosine is the x value on the unit circle. At 0 radians, the x value is 1. So this is really 1 minus 2, which is a negative number, less than 0. So negative in the first interval. Between pi over 3 and 5 pi over 3, there are many easy test values to use. Let's use a test value of pi over 2 because that just works out nicely. We know that the cosine of pi over 2 is 0. That's why I'm picking this one. So plugging in pi over 2, we have 1 minus 2 times the cosine of pi over 2. Because the cosine of pi over 2 is 0, this term is wiped out and we are left with 1, which is obviously greater than 0. So positive in this interval. Y prime is going to be negative in this interval. We don't have to think about it very carefully because at 0 and at 2 pi, cosine is in the same place. So cosine will have the same value. Since we only have one row, these are the overall signs of y prime: negative, positive, negative. Make sure you have memorized the graphical relationships between f, f prime, and f double prime. You should be able to draw this chart from memory in the margin of your next test or quiz in 30 seconds. For now, we need the fact that y will be increasing wherever y prime is positive and decreasing wherever y prime is negative. So y will be increasing on the interval from pi over 3 to 5 pi over 3 and decreasing from 0 to pi over 3 and from 5 pi over 3 to 2 pi. Here's how you write your answer with justification. We say y is increasing on the interval from pi over 3 to 5 pi over 3 because y double prime is positive. And y is decreasing on the interval from 0 to pi over 3 and 5 pi over 3 to 2 pi because y prime is negative. A quick word about abbreviations. In other videos, you will often see me use these abbreviations for increasing, decreasing, concave up, concave down, positive, negative, and because. But I need to be clear that you are taking a risk when you use abbreviations on the AP exam. That's because it's up to the discretion of the grader whether or not they accept your abbreviation. Most AP graders will accept these abbreviations. However, there's no guarantee. So if you want to be 100% safe, do not use abbreviations on the AP exam. However, if you're pressed for time, it may be worth the risk. For intervals of concavity and points of inflection, we need y double prime, the derivative of y prime. The derivative of 1 is 0, so we put nothing. We bring down the negative 2. And we move on to the derivative of cosine x. Memorize rule, the derivative of cosine x is negative sine x. However, I do not want you to write it like this. I've seen it 100 times. Students will often forget about the multiplication and end up treating this as subtraction, and the whole problem ends up being wrong. So when you are multiplying by a negative, I want you to take that negative and apply it to the front. In this case, this negative is going to change the existing negative to a positive. So y double prime is equal to 2 sine x. Now we need to find where y double prime is equal to 0, and normally I would say where y double prime is undefined, but sine x is defined everywhere, so we don't have to worry about that. We just need to set 2 sine x equal to 0 and solve. Dividing both sides by 2, we get sine x is equal to 0. Where is sine equal to 0? Sine is the y value on the unit circle, and y values will equal 0 at 0 and at pi. 0 is not included in the domain, so really we only have one critical value of pi. Set up your sine chart like this with your one critical value of pi on the top, and don't forget to include the limits of your domain. We really could have made one row of 2 sine x, and that would have been fine as well. We need to decide whether these factors are positive or negative in each interval. 2 is always positive, so we have that. Sine is the y value on the unit circle, so we know that sine is going to be positive in the first and second quadrants from 0 to pi, and we know that sine will be negative in quadrants 3 and 4, from pi to 2 pi. So sine is going to be positive in this interval and negative in this interval. The overall sign of y double prime will be positive in the first interval and negative in the second interval. We know that wherever y double prime is positive, y will be concave up, and wherever y double prime is negative, y will be concave down. So y will be concave up from 0 to pi, and concave down from pi to 2 pi. We say y is concave up on the interval from 0 to pi because y double prime is positive, and y is concave down on the interval from pi to 2 pi because y double prime is negative. Y will have a point of inflection wherever y double prime changes signs. And y double prime changes signs right here at pi. Kabam! Point of inflection. We say y has a point of inflection at x equals pi because y double prime changes signs. Let's use the information above to sketch the graph of y. First, we divide the graph into intervals based on the critical values that we found, pi over 3, 5 pi over 3, and pi. Now let's label y as increasing or decreasing in every interval. Y is decreasing from 0 to pi over 3, then increasing from pi over 3 to 5 pi over 3, and then decreasing again from 5 pi over 3 to 2 pi. Now let's label y as concave up or concave down in every interval. Y is concave up from 0 to pi, and then concave down from pi to 2 pi. In addition to this information, we need to mark where y has a horizontal tangent line. Y has a horizontal tangent line wherever y prime is equal to 0. That's at pi over 3 and 5 pi over 3. Let's put little horizontal marks at those values to remind us to form a horizontal tangent line at these values when we sketch the graph of y. I'm going to begin the graph of y with an open circle because 0 is not included in the domain. In this first interval, y needs to be decreasing and concave up and finish off the interval at a horizontal tangent line. So here we go. Decreasing, concave up, and finishing out at a horizontal tangent line. In the next interval, y needs to be increasing and concave up. No horizontal tangent line. So here we go. Increasing and concave up. In the next interval, y is increasing, concave down, and finishing out at a horizontal tangent line. So here we go. Increasing, concave down, and rounding out at a horizontal tangent line. Be careful in this last interval. 2 pi is the end of the domain, and 2 pi itself is not included, so we need to finish out with an open circle. So in this last interval, we need y to be decreasing and concave down. So we're going to go concave down and decreasing, but we're going to end with an open circle. Ooh, the next one is a rational function. The first thing we need to do is to find y prime. And this is a quotient, so we're going to need the quotient rule. Y prime equals. The poem for the quotient rule goes low d high less high d low. Draw the line and down below, the bottom squared will go. So let's start with that bottom squared part. X squared plus 3 squared. Now, how is that poem again? Low d high less high d low. When I say d high, I'm talking about the derivative of the numerator. When I say d low, I mean the derivative of the denominator. So low d high means first write down the denominator, that's low. And then d high is the derivative of the numerator, which is just 1. Less means subtraction, and then it's high d low. High is x, and d low is the derivative of the denominator, which is 2x. So this is y prime. I'm going to simplify this a little. Resist the temptation to cancel out the x squared plus 3 with one of the x squared plus 3's in the denominator. That is bad algebra. You cannot cancel out things that are connected by addition or subtraction. This 1 is not really doing anything, so I can just write x squared plus 3 without parentheses, and then we had this minus x times 2x, which is negative 2x squared. But these are like terms. X squared minus 2x squared is negative x squared. So y prime is negative x squared plus 3 over x squared plus 3 squared. Next, we need to find where y prime is equal to 0 and where y prime is undefined. A rational function will equal 0 when the numerator is equal to 0. So that's negative x squared plus 3 is equal to 0. Adding x squared to both sides, we have 3 is equal to x squared. I'm just going to flip this around. Taking the square root of both sides, we have x is equal to plus or minus the square root of 3. To be clear, this is two different critical values. X equals positive square root of 3 and x equals negative radical 3. A rational function will be undefined where the denominator is equal to 0. If your algebra skills are strong, you recognize right away that this equation has no solution. X squared plus 3 is always positive. The smallest that x squared can be is 0, and then that's going to leave behind a 3 squared actually, which is 9. So this expression will never be less than 9. It will never equal 0. If you wanted to sort of go through the motions, you would take the square root of both sides, and you would get x squared plus 3 is equal to 0. And then you would subtract 3 from both sides, and that would give you x squared is equal to negative 3. Maybe you would stop right here and go, well, there's nothing that you can square and get a negative number. Squaring something gives you a 0 or a positive number. Well, if you went one more step and tried to take the square root of both sides, that would give you an imaginary number. Set up your y prime sign chart with your critical values in order from least to greatest across the top. Make a row for the numerator and a row for the denominator. Be sure to label the chart as y prime. We need to decide whether these factors are positive or negative in every interval. Let's use a test value to decide whether negative x squared plus 3 is positive in the first interval. To the left of negative radical 3 is negative 2. In my mind, I'm thinking negative square root of 4. That's how I know it's to the left. So if we plug in negative 2 right here, we're going to have negative and then negative 2 squared plus 3. Be careful, some students get confused about the order of operations here. This is like multiplication with the negative in front, and then we have the exponent. I don't know if they still say PEMDAS to you guys, in Algebra 1 or middle school, but the order of operations. Exponents come before multiplication. So we have to square the negative 2 first, and that makes a positive 4, and then multiply by negative 1. So this is negative 4 plus 3, which is a negative number. In the next interval, let's use 0 as a test value. We can just do that mentally. If you plug in 0, that's gone, leaving a positive 3. In the last interval, let's use positive 2 as a test value. Well, you can probably see that's not going to change anything from when it was negative 2. Because if this is a positive 2, you still square this and you get 4, and then apply the negative and it's negative 4. So it's going to be the exact same thing. It's going to be negative. This last factor is positive in every interval. I mentioned earlier how this is always going to be positive because it's being squared and there's a plus 3 in there. So always positive. The overall sign of y prime will be negative in the first interval because of the 1 negative, positive in the middle interval, and negative again in the last interval. We know that y will be increasing wherever y prime is positive. So that's from negative radical 3 to positive radical 3. And y will be decreasing wherever y prime is negative. That's from negative infinity to negative radical 3, and from radical 3 to infinity. We say y is increasing on the interval from negative radical 3 to positive radical 3 because y prime is positive, and y is decreasing on the interval from negative infinity to negative radical 3 and from radical 3 to infinity because y prime is negative. To find the intervals of concavity, we're going to need y double prime. It looks like we're going to have to do the quotient rule again. Once again, the quotient rule poem goes low d high, less high d low. Draw the line, and down below, the bottom squared will go. The bottom squared is x squared plus 3 to the 4th power. So here we go, low d high. Low just means write the denominator down. So that's x squared plus 3 squared. D high is the derivative of the numerator, which will be negative 2x. Low d high less means subtraction, and then high d low. So that's negative x squared plus 3. That's high. Now, d low is the derivative of the denominator. We're going to need the chain rule in order to do this. So the chain rule says when you have a function inside of another function, first you take the derivative of the outer function. So this is me taking the derivative of the outer function. I move the 2 to the front and reduce the exponent by 1. You leave the inner function unchanged. So I'm going to have the x squared plus 3. But then you multiply by the derivative of the inner function, which is 2x. So all of this is the derivative of the numerator. Let's simplify this. So far, I put the negative 2x in the front, and if you multiply 2 times 2x, you get 4x, and I've put that in the front as well. We need to simplify this more, because after this we need to find where y double prime is equal to 0, and this is a mess. But notice that we have a factor of x squared plus 3 here and here. Because there's this common factor, I mean there's two of them right here, we can factor out x squared plus 3. In fact, let's factor out negative 2x and x squared plus 3. I'm pulling out this GCF of negative 2x times x squared plus 3. Now I need to decide what's left on the inside of the parentheses. To do that, sometimes it's helpful to think in terms of division. In my mind, I'm picturing it this way. If I divide the first term by my GCF, the negative 2x will cancel out completely, and then the x squared plus 3 from the GCF will cancel out one of the two x squared plus 3's. So that's still going to leave behind a single x squared plus 3. So that's what's left from the first term. Looking at the second term, the negative 2 will turn the negative 4 into a positive 2. Negative 4 divided by negative 2 is positive 2. The x's cancel each other out. Now, the x squared plus 3 will cancel out this x squared plus 3. And that's going to leave behind the negative x squared plus 3. So, what you see in the parentheses right here is what is left behind after we factor out this GCF. Distributing the 2, this part is negative 2x squared plus 6. To simplify further, notice that we have x squared plus 3, and we have x squared plus 3 to the 4th power in the denominator. These are connected by multiplication, so we can cancel out this x squared plus 3 with one of the x squared plus 3's in the denominator. That will leave behind 3 factors of x squared plus 3. Also, we have some like terms here. So we have x squared minus 2x squared. That's going to be negative x squared. And then we have 3 plus 6, which is 9. I'm actually going to flip this around as 9 minus x squared to make it more obvious that this is the difference of two squares and can be factored further. Simplified and factored, this is our expression for y double prime. Now it's time to find where y double prime is equal to 0 and where y double prime is undefined. A fraction will equal 0 where the numerator is equal to 0. And this numerator is equal to 0 at x equals 0 from the first factor, x equals negative 3 from the second factor, and x equals positive 3 from the third factor. A fraction is undefined when the denominator is equal to 0. Hopefully you can see at a glance that this little equation has no solution. X squared plus 3 cubed can never equal 0 because x squared plus 3 is always positive. The smallest this can be is 0 because it's being squared, it can never be negative. And so we have 0 plus 3 and then 3 to the third power. So 27, is the smallest number that this expression can be. If you went through the motions and tried to solve it, it would look like this. If you take the cube root of both sides, you get x squared plus 3 is equal to 0. Subtracting 3, you get x squared equals negative 3. Maybe right here you stop and realize that you can't square something and get a negative. That would be silly. But if you try to go even further and take the square root of both sides, you would get an imaginary number. So, no solution. Wait, back here I said x equals 0. X equals 3. I bet if I go back and look at the tape, I said 3 and wrote 0. Anyway, the three critical values are 0, negative 3, and positive 3. Set up your sign chart with your critical values in order from least to greatest across the top. It is up to you how many rows you want to make. I like to make a lot of rows because I find when I break it down into its smallest elements, it's easier for me to see what's going on. We need to decide whether these factors are positive or negative in every interval. Negative 2 is always negative, so blam, 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 blam. X will be negative to the left of 0 and positive to the right. 3 plus x is equal to 0 at negative 3. So really we only have two intervals to think about, to the left of negative 3 and to the right of negative 3. This factor will be negative to the left and positive to the right of negative 3. 3 minus x is equal to 0 right at 3. So this is the only place where 3 minus x might change signs. So to the left of 3, that's where we find numbers like 0. If we plug in 0 as a test, 3 minus 0 is 3. So this factor is positive to the left of 3. It's going to be negative for values to the right of 3. That's a big old negative sign. For example, if we do 4, this would be 3 minus 4, which would be negative 1. This factor is always positive for reasons we discussed earlier. The overall sign of y double prime depends on the number of negatives in each column. An odd number of negatives will make y double prime negative. An even number of negatives makes it positive. So y double prime will be negative in this interval and positive in this interval. We know that y will be concave up wherever y double prime is positive. So that will be from negative 3 to 0 and from 3 to infinity. Y will be concave down wherever y double prime is negative. So that's negative infinity to negative 3 and 0 to 3. We say y is concave up on the interval from negative 3 to 0 and from 3 to infinity because y double prime is positive. Y is concave down from negative infinity to negative 3 and from 0 to 3 because y double prime is negative. Y will have a point of inflection wherever y double prime changes signs. That happens at negative 3 and 0 and positive 3, all three critical values. We say y has a point of inflection at x equals negative 3, x equals 0, and x equals positive 3 because y double prime changes signs. Let's sketch the graph of y based on the information that we just found. First, we need to divide the graph into intervals based on all of the critical values we found. So that's negative radical 3, positive radical 3, and negative 3, 0, positive 3. Let's label y as increasing or decreasing in every interval. Remember, y is increasing between negative radical 3 and positive radical 3, and decreasing outside that interval. Now let's label y as concave up or concave down in every interval. Remember, y is concave up from negative 3 to 0 and from 3 to infinity. So that's these two intervals and this interval. And y is concave down from negative infinity to negative 3 and from 0 to 3. So that's this first interval and these two intervals. In addition, y will have a horizontal tangent line wherever y prime is equal to 0. So that's at radical 3 and negative radical 3. I'm putting little horizontal marks on these two values to remind us to form a horizontal tangent line as we approach these numbers when we sketch the graph of y. In the first interval, y is decreasing and concave down. So here we go, decreasing and concave down. In the next interval, y continues to be decreasing, but it switches to concave up. And at the end of the interval, it should be at a horizontal tangent line. So here we go, decreasing, concave up, and finishing out at a horizontal tangent line. In the next interval, y is increasing and concave up, no horizontal tangent line. So here we go, increasing, concave up, no horizontal tangent line. In the next interval, y is increasing, concave down, and finishes at a horizontal tangent line. So increasing, concave down, and rounding out at a horizontal tangent line. In the next interval, y is decreasing and concave down. So here we go, decreasing and concave down. In the last interval, y is decreasing but concave up. So we finish it off decreasing and concave up. And that's it. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.